Hello everyone. My name is Dr. Sok Jun Kwan working at KIST and KIST School. I'm a principal research scientist holding an associate professor at UST, who is a main instructor of this course. Welcome to the Lecture 5. In this lecture, I will introduce some selective advanced topics for nanotechnology. In Lecture 5, I will introduce some advanced topics for nanotechnology. These topics will be more important to use and understand the nanoscale phenomena as well as fabricate some advanced materials and structures. First, I will talk about the principles, brief history, applications, and types of metamaterials including metasurfaces. In this part, you will learn about how artificial structures can behave in a very strange manner. Second, I will talk about graphene nanophotonics including graphene nanoplasmonics. In this part, you will learn about why graphene is important materials for future nanophotonics. Third, I would like to introduce a certain kind of advanced nanomanipulator such as optical nanotweezers. In this part, you will learn about the basic principle of the optical tweezers and its applications to control the nanoparticles. Finally, I would like to wrap this lecture by commenting on the potential safety issues. This issue is very important for researchers including myself and you in the course of nanotechnology research and development. In particular, I will talk about the potential health issues given by the use of nanomaterials. The first advanced topic I would like to share with you is metamaterial. There is no clear definition of the metamaterials. In Greek, the word meta means beyond. However, let me define some critical properties of the metamaterials. Basically, they are engineered composites, and their physical properties are derived from their physical structure, not their chemistry. In particular, they normally have sub-wavelength structures, called metaatoms. They exhibit properties not observed in nature. They also exhibit properties not observed in their constituent materials. They are the composite material that is purposely engineered to provide material properties that are not otherwise attainable with ordinary materials. In principle, electromagnetic response of metamaterials can be described via effective electric permittivity epsilon and magnetic permeability mu, which are different from the base materials. These two properties of a function of the composing materials' properties as well as the composite structures. Based on the sign of epsilon and mu, we can classify the composites or materials into three classes. The first criterion is double positive materials, which have positive epsilon and mu. These materials are ordinary effective media. They are called as right-handed media. The second criterion is single negative or positive materials, which have opposite sign for epsilon and mu. They can be left-handed or right-handed. There are some artificial metals such as doped semiconductors and magnetic conductors such as ferrites exhibiting these properties. The third criterion is double negative materials, which have negative epsilon and mu. There are not natural materials satisfying these properties. They are left-handed media. One of the exciting properties for the double negative materials is their negative refractive index. Then what exactly the left-handed materials is? Actually, this question is firstly suggested by the Soviet physicist Vasilenko in 1968. Let us think about simple Maxwell equations. The epsilon and mu, let us replace them with negative ones as shown in the right equations. As can be seen from the equations, we can find that the original three-dimensional vector relationship is inversed. If you use your right hand, you can make your thumb, index finger, and middle finger for wave vector k, electric field E, and magnetic field H, respectively. However, for the double negative materials, you can use your left hand for K, E, and H, respectively. Therefore, we call the double negative materials as left-handed materials. The effective dielectric constant of the mixture EFF depends on not only the volume fill fraction but also the detailed geometric structure of the constituent materials. The simplest form of the effective epsilon is based on Maxwell-Garnett relationship as shown in the upper left figure. This relationship is based on the volumetric average with boundary condition considering the Maxwell equations field continuity. As shown in the lower left figure, there is another relationship called Brueggemann relation. This relation is different from the Maxwell-Garnett relation in that it considers the interconnectivity of one or two components inside the composites. However, we need more accurate model for the effective epsilon for the well-structured materials such as layered structures as shown in the right figure. In this structure, the effective epsilon is a function of propagation direction of the electromagnetic wave. For example, for the surface normal wave, the effective epsilon can be modeled using parallel connection as shown in the first equation. In contrast, for the surface transverse wave, the effective epsilon can be modeled using sequential connection as shown in the second equation. As shown in the previous slide, it is possible to control the effective electric permittivity of the materials by controlling the composition and structure. In addition, it is also possible to use symmetry and continuity of the materials in the composite. To design artificial double negative materials, it is important to design the structure. To understand the structure as a function of electromagnetic wave frequency, we can use RLC circuit model. Firstly, let us think about a simple metallic ring as shown in the upper left figure. We are assuming that magnetically active for electromagnetic waves with magnetic field is polarized normal to the surface. Then, oscillating magnetic field induces circular current in the metal ring. Diamagnetic response induced magnetic flux oppose the change in external flux by Lenz's law. Then, an array of sub-wavelength metallic rings will produce the effective magnetic permeability less than 1. However, if the circuit is purely inductive, there will be no resonance. This system is just L, inductor, circuit. Secondly, let us think about a little bit modified model which is a split metal ring as shown in the lower left figure. In this structure, there is a gap in metallic ring prevents the formation of complete circular current. At the end of the gap, electric charges accumulate across the gaps. This means the formation of non-zero capacitance in addition to the building inductor L. Therefore, split metal ring is basically LC circuit. The LC circuit has a resonance at omega sub LC, which is equal to square inverse. As shown in the right figure, our LC circuit satisfies the same equation as the mass spring system for simple harmonic oscillation. The component of resistance R makes the oscillation damping, and the damping constant gamma is defined as the ratio between the resistance R and the inductance L. Then, we can expect weak magnetic response when the electromagnetic wave frequency is much smaller or greater than omega sub Lc. And, at the omega sub Lc, there will be strong magnetic response. Therefore, we can expect negative effective index epsilon and mu at the very narrow window of frequency in the vicinity of omega sub Lc. Finally, we can think about further modified metallic structure which is composed of double split ring resonators, SRR, as shown in the right figure. This structure is proposed by John Pendry in 1999. In 1999, Pendry developed a theoretical idea to make magnetic permeability of materials negative using artificial structure for targeted electromagnetic wave frequency. Actually, Pendry is the first physicist who suggested the concept of the metamaterials. In conventional materials, the dielectric response derives from the constituent atoms. As discussed, negative or positive electric permittivity is possible over a broad spectral range. However, natural materials with a resonant magnetic permeability don't exist above a few terahertz. For example, ferromagnetic resonance in iron at microwave frequencies or antiferromagnetic resonance in MnF2 at 2 terahertz. This structure suppressed electric response. In particular, electric dipole moments of each rings cancel each other. This means that magnetic moment dominates in this structure. In addition, capacitance is more effectively introduced compared to single split metal ring. This can be optimized by several parameters such as slot width between two rings, large, and the cuts of each ring, small. 1 year later, Smith realized double negative materials for microwave as shown in the right. For the double negativity, Smith employed two distinctive structures. One is a lattice array of metallic rings and the other is thin metallic wire array. By combining these structures, both epsilon and mu become negative at very narrow window of the frequency. However, the negative permittivity and permeability due to electromagnetic resonance could be prohibitively lossy. For realistic applications, there are approaches for minimizing loss. One optimizing geometry limited success so far. To incorporate gain can achieve zero loss over broad frequency range, but difficult, complex, and expensive to realize in practice. 3 electromagnetically induced transparency, EIT, very low loss, but do not maintain negativity in the real part of mu and epsilon. If realized, they are narrowband and involve using 2 different types of metals. Pendry's idea and its realization works for electromagnetic wave at GHz range. For this range of the frequency, typical device size is few millimeters as shown in the left pictures. This is the first experimental realization of the artificial metamaterials with negative magnetic permeability as well as negative electric permittivity. However, at the gigahertz range, most of the instruments and signals can't be applied. This is mainly because of the fact that most of the useful frequency is beyond the gigahertz range. Fortunately, Maxwell's equations are scalable. This indicates that shrinking the double metal SRR size can lead to magnetic response at higher frequencies such as terahertz. This can be demonstrated by a simple relationship of the LC circuit resonance frequency omega sub residential is inversely proportional to square root of LC. In addition, both L and C are linearly proportional to the size A, and therefore, we can find that the frequency is inversely proportional to the physical size of the devices. This means that you can scale down the millimeter double negative materials artificial structures into micrometer scale, which is about 1/1000th. As shown in the left figure, the realistic size of the device size for the terahertz frequency was tens of micrometers. This means that we need some lithography process. Unfortunately, simple geometrical scaling breaks down at the frequency greater than 100 terahertz. This is due mainly to a fact that metals cannot be modeled as perfect conductor. There is an additional kinetic inductance of electrons, which is inversely proportional to alpha. This means that we can't apply the scaling down strategy for the optical frequency or visible wavelength range. Therefore, we need to design novel structure for the optical frequencies. For example, we can think of new geometries such as paired nanorods with lattice constant of 1 or 2 micrometers and fishnet lattice-like structures. In addition, we can think of metal strips array as shown in the left figure. In this structure, we can expect resonant magnetic response as a function of metal strip width. For example, broader metal strips provide negative magnetic permeability for asymmetric currents. However, there is non-resonant electric response. Therefore, narrower metal strips can act as a diluted metal with negative electric permittivity as shown in the right plots. Recently, researchers suggested fishnet structure for low-loss negative index metamaterials at optical frequency. In particular, this structure can support resonant magnetic responses and non-resonant electric responses simultaneously. This strategy corresponds to broader width and narrow gap of metal strip overlap. The overlap leads to the formation of metal strip lattice looks like a fishnet as shown in this figure. Therefore, fishnet structure can support low-loss negative index metamaterials at optical frequency. One of the fascinating aspects of the double negative materials is negative refractive index. Schuster suggested in this book entitled An Introduction to the Theory of Optics in 1904 by discussing the anomalous dispersion as occurs at any absorption band. In fact, the direction of wave propagation is determined by its phase velocity, while energy is transported at the group velocity. In fact, the negative refractive index is expected from the double negative materials or left-handed materials. First, wave is incident from ordinary right-handed material. Then, transverse component of the light wave vector k is continuous across interface. In particular, in the left-handed material, surface normal component k sub y must be negative to be consistent with sign convention. Using this sign convention, index ellipsoid for left-handed material must be negative, implying that the refractive index is negative. In here, causality requires pointing vector to correspond to forward traveling energy. Therefore, negative refractive index effect is observed as in the left figure. We can think of a variety of applications based on the negative refractive index materials. The first example I would like to share with you is the perfect or super lens. This device is beyond the conventional diffraction limit. For conventional materials with positive refractive index, there exists the diffraction limit. Due to this limit, evanescent waves cannot be collected by using conventional materials. However, in negative index media, evanescent waves grow exponentially along the propagation direction. Therefore, amplification of evanescent waves in negative index media can be done as shown in the right figure. This does not violate energy conservation, because evanescent waves carry no energy. Using the negative refractive index lens, we can make sub-diffraction limit image as shown in the upper and lower left figures. This means that we can obtain sub-wavelength image with enhanced resolution as shown in the lower middle image. In addition to the super or perfect lens, we can construct a hyperlens. Hyperlens is distinctive in magnifying performances. For example, its resolution is down to few tens of nanometers. In addition, it is adequate for far-field sub-wavelength imaging. To make the hyperlens, we can prepare hemispherical trench as shown in the lower left figure. On top of the trench surface, we can deposit several layers of silver and dielectric layers. The shape and the one-dimensional like multi-layered structures is advantageous in focusing light at sub-100 nanometers, and therefore, the resolution can be much more enhanced compared to a conventional optical microscope. Using the negative refractive index materials, we can control and manipulate the light in desired manner. For example, we can concentrate, split, half-transmit, bend, and swirl around the materials as shown in these simulated images. Along with the negative refractive index, it is possible to make artificial structure with the effective refractive index less than 1 but greater than 0. This artificial material makes group velocity of light varies inside the materials. This means that we can vary the optical path length of light inside the materials, to make the light have exactly the same phase. For the observers, this artificial material looks like transparent. Therefore, it is possible to make invisible cloak at specific wavelength or frequency. This is basically transformation optics. For example, we can think of metallic SRR-like structures arranged in circular manner as shown in the left figure. This structure can work as the electromagnetic cloak for microwave as shown in the right figure. However, for practical application of transformation optics, including invisibility cloak, low-loss metamaterials are required. The interesting thing about the electromagnetic cloak is its switching on and off performances. For example, we can control the geometric parameters of the artificial structures by applying external stimuli such as thermal, sound, electric, magnetic, and so on. By varying the parameters, we can control the phase and absorption coefficient of the artificial materials as shown in this figure. For the practical realization of metamaterials, we need low-loss materials beyond metal. As shown in this plot, we can think of some metal nitrides or perovskites for optical frequencies. In particular, transition metal nitrides are advantageous for the future metamaterials as well as long-wavelength plasmonics. First, they mimic the properties of gold at optical properties. Second, compared to gold or silver, they have high melting point. Third, they have much higher mechanical strength compared to conventional noble metals. They are also advantageous for plasmonic ceramics targeting 1. Solar/thermophotovoltaics. 2. Heat-assisted magnetic recording. 3. Photothermal therapy. 4. Nanophotonic circuitry and nonlinear optical devices. One of the most promising areas and applications of the metamaterials is metasurface. Metasurface is the surface structure for the light propagation with phase discontinuities. Without phase discontinuity, typical Snell's law is satisfied. Metasurfaces are essentially planar non-resonant metamaterials. However, with phase discontinuities, the law of refraction and the law of reflection should be generalized. As shown in the middle illustration, principle of least action tells us that the difference between blue and red path is 0. There are common ingredients for the metasurfaces. First, they should have sub-wavelength thickness. Second, they should be associated with flat composite structures. Third, the sub-wavelength structure should be engineered to control electromagnetic properties. Fourth, they should affect waves through modified boundary conditions instead of effective properties. Metasurfaces can arbitrarily control the following as a function of position: amplitude, polarization, phase, angles or phase, frequency, reciprocity such as nonlinearity, anisotropicity, and so on. As shown in the left figures, some array of metallic structure with designated symmetry and geometry can control the phase systematically. There are a variety of applications based on the metasurfaces. First, we can think of phase-controlled imaging such as hologram as shown in the left figure. Second, By controlling the phase as a function of the rotational angle of the surface to normal incident polarized light, one can construct a vortex beam as shown in the middle figure. Third, it is also possible to construct a flat lens as shown in the right figure. This lens is based on the optical path length control with the equivalent phase of the incident polarized light by the metasurfaces. In addition, there are so many potential applications based on the metasurfaces such as Huygens surfaces, color hologram, chiral spectrometer, nanocavity and laser, frequency selective surface, frequency conversion surface, broadband optical rotator, and nano antenna for plasmonics. Let me finalize the metamaterials by mentioning on the epsilon near zero, ENS, and mu near zero, MNZ, materials. Some materials show near zero index of refraction at certain frequency bands. By matching the resonances in series parallel circuit of a double negative index metamaterial, the propagation constant as a function of frequency continuously passes through zero index with a non-zero slope with non-zero group speed in its transition from double negative index to double positive index materials. Near-zero metamaterials are the structure composed of a periodic mesh of metallic thin wires, when its characteristic dimensions such as period and section of the wires are small in comparison to the wavelength, as shown in this figure, behaves as a homogeneous material with low plasma frequency. Let's think about the basic properties of ENS and MNZ materials. One light manipulation occurs with artificially designed metamaterial structure. Two ENS and MNZ materials have near zero parameters. 3. Therefore, their refractive index is also near zero. 4. Near zero refractive index means low wave number or vector, and hence no phase variation inside the medium. 5. This means that ENS and MNZ materials behave with static-like character even when dynamically oscillating. One of the fascinating performances by the ENS and MNZ materials is tunneling. 1. For ENS, both electric field and power are compressed into the channel. 2. Phase constant. 3. They are independent of bending due to supercoupling. 4. Supercoupling basically emerges from the combination of a constant transverse magnetic field, produced by the enlargement of the wavelength in ENS media, and the associated reduction of the magnetic flux induced by narrowing the channel, which, in turn, imposes a zero circulation of the electric field and enforces full transmission. 5. For MNZ medium, tunneling will be observed if the height of the channel is substantially increased. 6. MNZ acts like an electromagnetic point, thus seemingly directly connecting the input and output ports and enabling full transmission. I would like share some perspectives on the metamaterials for future nanophotonics. Unleashing the full potential of hybrid nanophotonic components for on-chip optical communication by leveraging the ability of metals to perform simultaneous electronic and optical functions. There are a variety of types of interconnects. In addition, there are different modules such as optical processing of data, sub-wavelength confinement, electrodes are in place, coupling to other on-chip devices, combination of guiding, detection, modulation, sensing, usage of field enhancement for nonlinear optics, integration with optoelectronics, lab on a chip, solar cells. For nanolasers, plasmonic waveguide and its interfaces, detectors, modulators, metamaterials and metasurfaces can be widely applied. In addition, for nanoimaging and spectroscopy purpose, there are some critical modules such as data recording and storage, sensing, SIRS, sub-L photodetectors. And these modules can be further enhanced with an aid of metamaterials and metasurfaces.